Hello students, imagine power being generated at a dam hundreds of kilometers away, yet the lights in your home glow instantly when you switch them on. How is power transmitted so efficiently over such long distances? The secret is transformers. A transformer is a device that changes AC voltage from one value to another. It works on the principle of mutual induction. Two insulated coils are wound on a common soft iron core. The primary coil receives the input AC voltage and the secondary coil gives the output. The alternating magnetic flux in the core links both coils, inducing EMF in the secondary. That's the essence of a transformer. Let's explore how transformers create voltage in their coils. Have you ever wondered how your phone charger steps down to 130 volts AC to just 5 volts? The answer lies in electromagnetic induction between the primary and secondary coils. We start with the concept of magnetic flux. Suppose the magnetic flux per turn is phi of t. Now, in the secondary coil, the induced EMF is given by Es equals minus Ns d phi by dt. Here Ns is the number of turns in the secondary. The negative sign reminds us of Lenz's law. The induced EMF always opposes the change in flux. Similarly, in the primary coil, the back EMF is given by Ep equals minus Np d phi by dt, where Np is the number of turns in the primary. For an ideal transformer with negligible resistance and leakage, the induced EMF in the primary approximately equals the applied voltage Vp, and in the secondary it equals Vs. So, Ep is approximately Vp and Es is approximately Vs. Quick insight, this means that the induced voltage is directly proportional to the number of turns in the coil. That's why increasing or decreasing turns changes the voltage levels in a transformer. It's the core principle behind stepping up or stepping down electricity safely. Hello everyone. Let's now connect the dots between the primary and secondary sides of a transformer. Imagine a seesaw. When one side goes up, the other comes down. Transformers follow a very similar balancing act between voltage and current. Using the EMF equations, the ratio of secondary voltage to primary voltage is equal to the ratio of number of turns. That is, Vs by Vp equals Ns by Np. More turns in the secondary means more voltage induced. But energy is never lost, power conservation always holds. This means Vp multiplied by Ip equals Vs multiplied by Is. In other words, if the transformer raises the voltage, the current must reduce to keep power balanced, and vice versa. Combining these, we get Vs by Vp equals Ns by Np and Is by Ip equals Np by Ns. So, the voltage ratio follows the turns ratio and the current ratio is the inverse. Quick insight, this is why step-up transformers increase voltage but at the same time reduce current. That's exactly how power can be transmitted efficiently over long distances with minimal loss. Have you ever wondered how electricity generated in a power plant travels hundreds of kilometers and still reaches your home at safe usable levels? The secret lies in transformers, the unsung heroes of power systems. Let's look at the two main types. First, the step-up transformer. Here, the number of turns in the secondary coil is greater than in the primary coil. This raises the voltage. Vs becomes greater than Vp, but in return, the current is reduced. Step-up transformers are what allow power plants to boost voltage to extremely high levels for long-distance transmission with minimal losses. Second, the step-down transformer. In this case, the secondary turns are fewer than the primary turns, lowering the voltage. Vs is less than Vp, while increasing the current. This is the kind of transformer that brings the voltage down to safe levels before it enters our homes. Let's take a simple example. If the primary has 100 turns and the secondary has 200 turns, the ratio 200 by 100 gives us Vs by Vp equals 2. That means a primary voltage of 220 volts at 10 amperes can be transformed into 440 volts at 5 amperes. Notice how power remains conserved, voltage goes up, current comes down. Quick insight: this simple principle is behind almost everything, from power transmission grids to the tiny adapters that charge your phone. Imagine pouring water through a pipe, but some of it leaks out before it reaches the other end. That's exactly what happens in transformers. Not all the energy makes it to the output. Let's explore the main causes of these losses and how engineers minimize them. First, flux leakage. Not all magnetic flux links both the primary and secondary coils. Some of it escapes, just like water seeping through cracks. By carefully overlapping windings, this leakage is reduced. Next, the copper loss. Heat is generated due to the resistance of the windings. We call it I²R loss. The solution? Use thick copper wires to keep resistance low and efficiency high. Then comes the eddy current loss. When the alternating magnetic flux flows through the iron core, it induces circular currents inside the core itself, wasting energy as heat. To fix this, the core is laminated into thin sheets, preventing large eddy currents from forming. Another is the hysteresis loss. The core is magnetized and demagnetized again and again, which consumes energy. By using low hysteresis steel, this loss can be minimized significantly. Quick insight: thanks to these engineering improvements, well-designed transformers can achieve efficiencies above 95%, meaning almost all the power you put in comes out useful.
Hello students! Let's take a practical example to see how power and power factor work in a transformer-like system. We're given the number of primary turns, NP, equals 400. The number of secondary turns, Ns, equals 2000. The primary voltage, Vp, is 220 volts, and the primary current, Ip, is 5 amperes. Step 1. We calculate the turns ratio. Ns divided by Np equals 2000 by 400, which is 5. This means the transformer is stepping up the voltage by a factor of 5. Step 2. Let's find the secondary voltage. Versus equals Vp multiplied by Ns over numbers substituting the values. 220 multiplied by 5 gives us 1100 volts. Step 3. Now, power input equals power output, assuming an ideal transformer. Power, P, equals Vp multiplied by Ip, which is 220 times 5, giving 1100 watts. Step 4. Let's find the secondary current, is equals P divided by Vs. That's 1100 divided by 1100, which gives 1 ampere. So what do we learn from this? Step-up transformers raise the voltage but reduce the current, while keeping power conserved in the ideal case. This principle is exactly why we can transmit electricity efficiently across long distances with minimal losses. Quick insight: higher voltage with lower current means reduced I²R losses in the transmission lines. Have you ever thought about how electricity generated at a power plant actually reaches your home? The journey of electricity is a fascinating story of efficiency and smart engineering. Electricity is typically generated at around 11 kilovolts in power stations. But to send it across hundreds of kilometers, this voltage is stepped up to hundreds of kilovolts using massive step-up transformers. Why? Because higher voltage means lower current, and lower current reduces I²R losses in the transmission lines. That's the secret behind efficient long-distance transmission. As the electricity approaches cities and towns, it can't be delivered at such high voltages. It would be unsafe. So, at substations, step-down transformers carefully lower the voltage. Finally, for domestic supply, the voltage is standardized at 240 volts, delivered safely into our homes and offices. Step-down transformers play a key role here, making sure it's just the right level for household appliances. So, in essence, step up for transmission efficiency, step down for safe distribution. This combination is what makes large-scale power delivery not only possible, but also reliable. Quick insight: without transformers, transmitting electricity over long distances would be almost impossible. The losses would be enormous. So, let's wrap this up. Transformers work on mutual induction and only with AC. The voltage ratio equals the turns ratio, while the current ratio is inversely proportional. Step-up transformers increase voltage but reduce current. Step-down transformers do the opposite. Despite unavoidable energy losses, efficiency remains very high. Most importantly, transformers make long-distance power transmission possible and economical. Without them, our modern electric world would not exist. I hope this session clarified the role and working of transformers. In our next discussion, we'll explore how AC circuits behave under resonance and why it's so important in communication and technology. See you then.